Welcome to Radiance webinar on measurement solutions for vehicle interior and exterior lighting. I am Mike Naldrit. I'm a sales manager with our automotive sales team. I've worked in the automotive industry for 20 plus years at the tier 1 and tier 2 level, and I look forward to sharing this material with you. So, quick rundown of our presentation today. We'll do a quick introduction of Radiant, and then we'll talk about measuring light through various applications around the vehicle, including headlamp measurement, LED source characterization, LED strip uniformity, backlit symbols and shapes, reflection scatter, and our enhanced color calibration. And we'll also spend a couple minutes just talking about near infrared measurement. At the end, we'll have a live Q&A session. So as we are going through the presentation, you will notice there is a Q&A button on your toolbar. So please go ahead and enter those questions as we go, and we will cover them at the end with you. So let's get started. So Radiant Vision Systems, a part of the Konica Minolta family since 2015, and is a leader in light and color measurement solutions. We supply a wide range of hardware and software solutions to a variety of industries for both R&D and production end-of-line testing. Our global headquarters is in Redmond, Washington, not far from the Microsoft campus, and we have locations around the world to support your facilities at R&D, production, or your suppliers. So imaging photometry. We provide measurement solutions that replicate and quantify human perception of brightness and color. And of course, quantify is the important term here, because what we want to do is provide analysis based on objective numerical data. If you work in color, you're probably familiar with the CIE color chart, the 1931 or 1976 version. This happens to be the 1931. And this is a grid that allows us to plot the visual perception of what the average human eye can see. Unfortunately, displays and technologies cannot reproduce the full color space. So the subsegment that they can produce, we call color gamut. And that color gamut is a triangle produced by TRISTIMULUS color system, you know, the corners located by the primary RGB colors of that display. And of course, the rest of the colors of that display or technology are a mix of the three within that gamut or triangle. So why is that TRISTIMULUS important? Well, that's because that's what we're trying to replicate with our colorimeters that we'll discuss in more detail later. But we use a color filter wheel to precisely match CIE TRISTIMULUS curve, which allows us to have NITS traceable results. So let's talk about our portfolio. We have two main series of systems for imaging. So on the left, you'll see our Y series imaging photometers, and on the right, our I series imaging colorimeters. They come in a range of resolutions from 2 to 43 megapixels. Right? And you'll notice the colorimeter on the right is larger to accommodate that rotating TRISTIMULUS color filter wheel that we just discussed, as well as a neutral density filter wheel. So let's take a look inside of that colorimeter. First up, our lenses are electronically controlled to simplify use. As I just mentioned, we have the precision TRISTIMULUS color filter wheel and also a neutral density filter wheel for expanded dynamic range to measure very bright sources. Next is our scientific grade image sensors in the variety of resolutions. But importantly, those image sensors are cooled by a thermoelectric cooler in order to maintain the optimal operating temperature. That reduces thermal noise, improves accuracy, giving us a very high signal to noise ratio for much better data. And the systems are NITS traceable calibrations. So we use electronic lenses of various lengths to suit the application and field of view. These lenses are factory calibrated for any focal distance for color shift, color calibration, flat field. We can also control them electronically through our software for both the focus and f-stops, allowing these to be changed easily and automatically through test sequences. So the other half of the equation is the software. And so one of our primary packages is TrueTest, which is a comprehensive test suite. It allows you to measure luminance, color, uniformity, but other more difficult analysis, detailed analysis like pixel and particle defects and Mura or blemish. Today we'll also be talking about our ProMetric headlamp module, or PMHL, specifically for measuring headlamps against various regulation standards. So one of the great advantages of TrueTest is the ability to run automated inspection through multiple analysis, multiple measurement images with one click. But both TrueTest and PMHL in the end give you an evaluation based on objective numerical data that you can set pass-fail criteria against. And our SDK and APIs allow you to fully integrate the system into your production control systems or video pattern generators. So let's talk applications. So because of our flexible hardware and software options, we cover a wide range of automotive applications across displays, from center console to head-up, as well as any backlit device in the cockpit, in the instrument cluster, or center stack. For today, mostly we're going to be focusing on the lighting applications, from DRL signals, headlamp, tail lamp, interior ambient lighting, and also bare LED sources. And of course, the future is changing. We see lots of new technologies moving into automotive lighting. For example, OLED has been making the shift after being proven out in consumer applications into automotive, like the Cadillac Escalade displays, for example. But even in lighting applications like the tail light concept we see here on the left. And obviously, micro LED is a hot topic these days that we're seeing even in lighting applications. So I won't be covering measuring these two technologies specifically, but just know that the systems we're talking about can measure these technologies today, and we are supporting customers both in consumer and automotive for measuring these new and advanced technologies. So headlamp measurement. As I mentioned, we have a specific module for measuring headlamps, and that is our ProMetric headlamp module, or PMHL for short. And this software package allows you to measure headlamps against the various automotive lighting standards. So we have those standards built into our software. The most popular regulations from ECE, SAE, and IIHS. So with our imaging approach, we're doing a reflective setup off a diffuse coated wall or screen. So you can see a typical setup in the photo on the right. But before measuring lamps, we start with a flat field calibration using an ILLUMINANCE calibration source. This allows us to eliminate any defects in the wall and help remove any impacts of the wall's distribution so that we are just measuring the source. And we have a nice easy wizard to walk you through the steps to create that field calibration. You can see a screenshot of the wizard right here. So instead of measuring luminance values, now we'll be measuring illuminance, typically in lux. One of the great features of PMHL is its ability to automatically place and align those standard regulations through our POI tool. It allows you to automatically align those based on gradient, elbow, or coordinates. So you don't have to take your measurement and try to manually align those standards. We can do it automatically for you. And here's what that looks like. So we see the true color measurement on the left and false color on the right. And so we have loaded up the R123 regulation, aligned it, and received the results there. Unfortunately for this guy, we have 1 point failing, but it's better to know that now. The advantage of this approach is speed. So we can capture these images and analyze them in seconds as opposed to 30 minutes or even hours with a goniometric system. So this gives you a way to measure a lot of parts very quickly, whether you're measuring 30 or 50 samples for DV, or it's a production application where you're very concerned with takt times. This is a very fast approach to measuring headlamps. So here we can see another standard we've loaded into our POI system, the R112, and what it looks like overlaid with an actual measurement. Unfortunately, not all of us have the space to measure a headlamp beam. It takes quite a wide wall. So for cases where you're limited in your lab, PMHL has the ability to take multiple images of the headlamp. So for example, if we rotate the headlamp to 3 positions, you can see here we've taken 3 images or measurements. Each of those measurements was centered at 0 degrees. But then through PMHL, we can then add an offset to those left and right images. So in this case, they had been offset by plus and minus 30 degrees. And then PMHL will analyze each image or section individually, and then the results are combined into one synthetic image. And even if you have to break up your measurement into 3 pieces like this, it's still quite fast since we're only using several seconds for every measurement. PMHL also gives you the ability to convert illuminance to intensity based on projection distance. So you can see that tool here. In the top, we have our original illuminance measurement, and it's been converted to intensity below. Then we can take that intensity a step further to road illumination. So we can take that 2D info and the working distance and extrapolate a bird's eye view of that road illumination. And you can also overlay isoplots for intensity over distance. We also give you the ability to export the data out of PMHL. So for example, you can export to an IES or IMDAT file, which can be convenient if you want to take our 2D imaging data and correlate it against existing goniometric data that you may have. And you can also create 2D and 3D isoplots in order to illustrate beam distribution changes. And of course, through the software, you can customize the plot colors and scales and export them or custom or cut and paste them into your reports. Okay, so let's take a quick look at PMHL in action in this short video here. So here we're going to see the 2D measurements. You can look at it in true color or in false color for intensity. You can adjust the scale or apply a log scale, overlay a grid. And if we go into define points of interest, this is where we can load up the various built-in standards. So we can load any number of standards that we would like to apply to the measurement. So if we go back up and open the measurement, now we can overlay that standard. And here we can see the lower zone is outlined in red. It's failing, but actually we haven't done the auto align yet. So if we click on the auto aim button, we have realigned it according to the gradient. So we can see the lower zone has passed, but the upper zone is now out of spec. Now we can take a look at a road illumination plot. Again, you can overlay a distance grid on top of that, or look at it in true color. As you move your cursor around, it's going to provide you data of that actual cursor point. So you can see the lux of that point, or the CXY coordinates, and the distance. So a very, very powerful tool to simplify headlamp measurement. So next, we are going to go on to LED source characterization. And this can be LEDs for headlamps, for backlit components that you want to take a look at, or if you want to do LED binning. The traditional methods of measuring LED sources, like a goniometer or illuminance on a wall, like we were just looking at for the headlamp, not really suitable for production applications when you're trying to look at hundreds, if not thousands, of LEDs. So a better approach is direct imaging. The benefits of a direct imaging approach is we are able to capture and evaluate multiple hundreds of LEDs in a single measurement. Our software will automatically find and isolate every LED, regardless of its position or orientation, and then allow you to run pass-fail criteria for brightness, color, intensity, find stock on or stock off LEDs, and look at the uniformity across the entire array. So this can be very useful if you want to do further LED binning. Most likely that you buy LEDs already binned, but even within one bin, the luminance and color can still vary up to 30%. So we're seeing more and more customers do on-site additional binning at their facility by measuring the LEDs in this direct approach, doing further sorting. And again, you can still check for bad LEDs at this point, rejects due to phosphor issue, cracking, etc. So the big advantage of this approach is it can be done much, much faster than alternative measurement methods like fiber optic based systems or integrating spheres, because you can measure hundreds, if not thousands, within one image. So you can also do LED intensity. So like before, it can locate and isolate each individual LED and calculate the intensity and the intensity uniformity across the strip or array and dominant wavelength. And so we're going to take a quick look at a video that shows how we measure bare LEDs. So we're going to run through a sequence of different tests here with individual strips of LEDs and also multiple strips of LEDs. And you can see how quick it is taking each measurement and analyzing. So the first one, we see each LED isolated. The next one is an example of the strip being rotated, but still being able to capture the data. Here we have a missing LED. So through our point of entrance count, we see that the number is too low and it's been failed. And here we have an example of our chromaticity being out of spec. And here we see multiple strips being captured at one time very quickly. So this is drastically faster than other approaches. Gets you really good tact times, the ability to measure hundreds and hundreds of LEDs at once. So as we move from those bare LED strips, let's look at them after they've been put into a module or behind a diffuser. Of course, there's multiple applications around the vehicle on the interior and exterior. These days, we're seeing a lot more light, ambient light, especially used in the car, not only just according to certain brand colors, but a lot of color mixing today, either based on driving conditions for warning or alerting drivers, but just user preferences, being able to change those colors to what you like. But this just makes it that much more difficult to get good color matching around the interior space. But that's why we're here to help. So our TrueTest software can account for any shape, any size, so we can easily get the luminance and color data for that diffused LED light, bezel, or strip. We also give you tools to measure values along a defined path directly in the software and measure deviation along the path as well. So this is an example of an interior light strip. So on the left, you see the false color image, and we have drawn a multi-segment cross-section path through the center line of that strip. And on the right, you see the cross-section data for luminance. And so, of course, the luminance data is matching what we can see in the false color image. It looks to be getting gradually brighter from left to right. And we can provide you multiple data for that cross-section path. And of course, we can do the same thing for exterior light strips, whether it's a DRL or a signal. So now we'll take a quick look at a video of measuring that lamp light strip. So we have two main methods. One is that cross-section profile, or using our point of interest tool. So first, the cross-section path. So here we'll draw a custom multi-segment line because of the shape of this light strip is a little complex. So here we zoom in, look at the false color image, and draw a line down the center of this light strip. And now you can see that luminance data in the chart. It's a little noisy, so what we can do is thicken the line or average the data. And so that cleans it up a little bit for us. We can change the scale as you need and also export these results to Excel for further analysis or reporting. The other way is POI. So if we run the sequence on that same strip, we have pre-created a POI set, which is a group of circles. A little difficult to see, but we have green circles running through that strip. And that allows us to average the data within those virtual detectors or circles. And so we get the data for every circle individually, and we also get the data for them as a group. And as always, you can set pass-fail criteria to automatically find those failures. So this is a great and quick and easy way to measure the performance of your light strips. Certainly a lot easier than moving a spectrometer and taking multiple measurements. So now I'm going to briefly touch on backlit components within the cockpit. If you missed it, we recently had a webinar that did a deep dive of this topic. So if you're interested, look on your website. It's called, our website. It's called Truly Automated Light and Color Measurement for Telltales and Indicators. So it'll go much deeper than what we'll cover today, if that's your interest area. So of course, a lot of backlit components and symbols around the cockpit. TrueTest and our Auto POI allow you to measure inter and intra-symbol uniformity, luminance and chromaticity, as well as character orientation and symbol defects. So let's just take a quick look at our Auto POI tool. Big benefit of Auto POI is that it is automatic. So if you look at the kind of traditional method on the left, you've got a static POI that's capturing a lot of space outside of the illuminated character. But through our thresholding techniques, we're able to isolate just the illuminated portion, and you can see it outlined in the image on the right. And so now we're just providing data on those illuminated portions, and that all happens automatically in the software. So here's an example of a cluster emitter. So it's been measured and Auto POI applied, and each character we want to measure has been outlined by the software in yellow. Each one's given a number, and you get the results in an analysis results table that you can see in the bottom right here. So you can pass-fail every individual tick and number. And Auto POI gives you the tools to threshold or isolate the pieces you want to measure, or apply different criteria to different colors, for example. So you see the measurement image on the right. And as we move from right to left, we apply different thresholding techniques. So The first one is just thresholding on luminance only. So you can see the POI map that's been extracted is just those illuminated characters that we can see in the measurement image. We can take that a step further and threshold on color as well. So here we've extracted the metric speed dial. And we can also then further threshold on size. So here we've extracted the characters and we no longer have the dots or tick marks. So this allows you to really focus in on what you want to measure or apply different pass-fail criteria. This is a very powerful tool, much easier than moving a spectrometer around again to try and take individual measurements. So if this looks interesting to you, I highly recommend you check out our other webinar or give us a call. We have also recently introduced our VIP, Vision Inspection Pack. So this actually takes our auto POI a step further. So our previous auto POI allowed you to take the typical light and color measurements. VIP takes it a step further by integrating more computer vision type techniques that allow you to inspect the integrity of the symbols, shapes, or text. And it all happens within one image. So you no longer need to have two separate stations or two different pieces of equipment, one for light and color, one for defect inspection. So we have responsive registration to look at those symbols in order to understand how they should look and be positioned. And that allows us to run the detection of defects for inclusions, exclusion, deformation. So, for example, if we look at the measurement we've captured of this airbag icon, so we have a standard green POI applied here. So we could pass-fail on just that. But with VIP, we can capture this whole symbol. We understand through the initial learning process what it should look like. And so now we can fail based on the entire symbol. Our responsive registration allows us to move these POI points. So even if the symbol is rotated, we can still place these point of interest measurements or virtual detectors where we want them to be automatically. And the big benefit is adding this advanced defect detection. So not only just light and color, but inclusions, exclusions, deformations, as you can see in these examples. And then you have the full control over the criteria for what's acceptable and what's not from size and light and color perspectives. So let's just talk a little bit about lighting effects. Unfortunately, with all the lighting around the vehicle, we can sometimes have the unwanted consequence of light scatter or reflections. So just so you know, our systems can measure those reflections as well. Because of course, we don't want that distracting from the end consumer experience. And so with the same equipment, we can measure those reflections as if they were a light source. And you can get your typical luminance data, or maybe even more importantly, delta luminance, in order to understand with the light source off and with the light source on, what's that difference in luminance look like. All right, and now on to enhanced color calibration. What is enhanced color calibration, or ECC for short? Well, as a standard with our systems, we include an illuminant A calibration. Enhanced color calibration, or ECC, is our proprietary factory calibration to get you much greater out-of-the-box accuracy for narrowband sources. So this is an optional add-on, and what it includes is LED calibration for narrowband calibration. We also provide you tools for enhanced one-color calibrations, and so as standard we include a one-color cal for white phosphor LED, but you can make any number of your own user-made one-color calibrations. So the advantages of the ECC is it's much more accurate than our illuminant A calibrations for narrowband LEDs. So that means right out of the box, it's going to be much more accurate for luminance and color. For one color calibrations, they're much more robust, meaning they are more accurate over a larger color space area, as you can imagine with the bullseye here. So instead of just being accurate at the center, you're accurate across the entire dartboard, for example. And because they're much more accurate over a larger area, that means you need to do fewer of them. So our LED narrowband calibration is included, great for LEDs and LED-backlit devices, for narrowband single color LED sources and primaries of RGB. So right out of the box, this gives you accuracy in line with several competing spectrometers, but with all the advantages of an imaging system. And also included, again, is the white one color calibration for the white LED, either for the LEDs themselves or backlit units. And as I mentioned, the one color user-made color calibrations are more accurate over a wider color area, making them more robust. But also embedded in our ECC is our patented adaptive calibration. So this allows you to create a library of one color calibrations and then apply multiple calibrations to one measurement, and then expanding that color accuracy area even larger. And so here are the results comparing our narrowband color LED ECC against a reference measurement device. So here you can see on luminance, we're showing 5% or less variance. You know, with our typical illuminant A calibration, you can see that variance be up to 25% or greater in the color space CX/CY. You can see variance up to 0.0048, where with an illuminant A calibration, you're looking more in the range of 0.015. So this drastically improves the out-of-the-box accuracy, and those user-made one color calibrations get you that much greater color space coverage. Our final topic for today is our solution for measuring near-infrared sources that we call our NIR intensity lens, or NIRI for short. So this is a one camera, one lens solution, which allows you to measure sources around 940 nanometers. The camera is coupled with a conoscope type lens that allows you to simultaneously measure all angles of the emitter up to plus minus 70 degrees at a resolution of 0.05 degrees per sensor pixel. So the applications we're seeing in automotive right now, the most common are for emitters used in the cockpit for either facial recognition, eye tracking, or gesture tracking. So you could use a goniometric system or reflective type measurement, but the advantage of our NIRI solution compared to gonio, of course, is that we're capturing all that data in one image. And our TrueTest NIRI software module gives you the tools to be able to evaluate different types of sources, whether it's a flood or dot source or some kind of structured light pattern in run, pass, fail against those analysis. So it's much, much faster than other techniques and with much higher resolution. So if you'd like to know a little more about that than what we shared today, please feel free to reach out. And so that brings us to our Q&A session. So as a reminder, if you haven't already put in a question, you can still do that by clicking the Q&A button on your toolbar. I would like to introduce our Q&A panel for today. So besides myself, we have Matt Schultz, Automotive Business Leader, and Brett Stonebridge, another sales manager on our team. Welcome, Matt and Brett. Thank you for joining us.
Hey, Mike, and this is Shana from the marketing team. Just hopping in.
Yes.
I wanted to just.
Hi, Shana.
Hey, I'm just in the background. I'm going to be fielding some questions to you guys. Mostly I'll direct those at Mike, but Mike, if you want to call out anyone else to help answer a question, please call out Brett or Matt. I see some questions are coming in, and in case anybody missed it, there is a Q&A widget on your control panel in Zoom. If you'd like to ask a question of the team about light measurement, please feel free to send us a question, and I will read those over to Mike. So, Mike, I have the first question here I'll ask you is, can headlamps and light strips be measured simultaneously? I think in thinking of like both in one headlamp, for instance, or what might be the case?
Yeah, so I would say generally no. I think for a headlamp, typically we're trying to measure against those various standards, and that would be done in the reflective wall setup that we looked at, where if you're looking at a strip, generally you want to do that in a direct measurement with the camera looking directly at the headlamp. So I think we would suggest those normally be done separately.
Okay, great. Can you explain when you would measure a light directly versus on a wall?
Okay, yeah, so that's kind of similar to the previous question. So when measuring on a wall, we're generally interested in what that projected distribution of the source looks like. If we're taking a direct measurement of a LED or lamp source, then we're looking at it as a point source or a point intensity. So it depends on the type of data that you're trying to achieve. So whether it's you're looking for that projected distribution or the point source characteristics.
Okay, great. I had a question come in through text and also on the Q&A here. Is there a standard method to prepare a diffused wall to test a headlamp, or is there any standard ready-made board surface that might be available for testing on a wall?
Yes. I don't know if there's any specific standards, so if Matt or Brett know of any, they can jump in.
Yeah.
But you do want a, oh, go ahead.
Oh, sorry, Mike. Yeah, sorry, I can jump in here. So we do actually offer a couple different things here, diffuser-wise and paint recommendations. I don't have them on hand for the actual name of them, but it's something we can forward on offline. But it's definitely a setup we've walked through several different times.
Great,
Okay, thanks, Brett.
Thanks, Brett. There's another question here. How would I measure the illuminance of a headlamp beam to see how it's projected on a roadway?
Okay. Let me back up for a moment on the presentation then, because I think we have a slide to illustrate that. So actually that is built into PMHL. So after you've taken your normal illuminance measurements, we have a built-in tool that allows you to convert that to road illumination that you can see on the slide here, based on the working distances. So that's built right into PMHL for you.
Great. Another question here, what kind of field of view is needed to measure an entire headlamp beam, or how is it set up?
Okay. Generally speaking, the field of view is dictated by the lamp itself. So the beam needs a certain distance in order to fully form on the wall or screen. So that distance and its spread will determine the kind of the horizontal field of view that's needed, and we can match our camera lens to cover that field of view. It can be the distance can be as short as several meters, but actually some standards call out, for example, that the lamp needs to be 25 meters from the screen. But one of the nice features of PMHL is you can take those measurements closer at 10 meters, for example, but then extrapolate that data back to 25 meters. So if you don't have the wall that's wide enough to move back to 25 meters, we can get you that data.
Okay, great. Thanks, Mike. For light strips or shapes, kind of similarly, how large of an area can be measured? For instance, if you had like a light strip on a DRL in a headlamp or other size.
Okay. So actually we can measure quite long light strips, even more than what you might see in a typical DRL, especially a more traditional DRL that's in the lamp. So for example, we're working with customers on testing light strips that are as wide as the car. So maybe you've seen in some concept cars, more and more you see decorative light strips across the entire front of the car or rear of the car. And we can easily characterize those light strips with the right lens for the field of view and the right camera for the resolution.
Great. A question came in about the ECC, if that is done at our lab in the factory or if it's done at the customer site.
I'm sorry, say that one again?
Sure. Regarding the ECC calibration, is it a factory calibration done at our lab, or is it done at the customer?
Yeah. Okay, yeah, thanks. Yeah, so part of it is a factory calibration. So there's the two pieces that are included out of the box. So if I just back up a little bit here in the slides, let me bring that up again. So it is a factory calibration. And so we provide you a narrowband calibration for measuring luminance with very high accuracy out of the box. And then we have the capability for users to create their own one color calibrations on site with their own sources. We include one for white phosphor LED sources, but if you're using a different type, then you can freely make as many other user-made one color cals as you need.
Okay, great. And this is kind of on the same topic. How accurate is ECC calibration out of the box?
Okay. Yep. So again, I can jump to that slide. I can just share that data again, and we'll be posting these slides after the webinar. If you'd like to deep dive this accuracy a little more, encourage you to take a look. So like I said, we're in line with several competing spectrometers for those luminance numbers for the out of the box. And the one color cals really expand the color range that you are able to maintain accuracy. But if there's follow-up or you'd like to know a little more detail about that, feel free to reach out to me.
Okay, great. A question on I think the cross-section tool. Can multiple light strips or cross-sections be measured simultaneously?
Yes, absolutely. So today in TrueTest, you can look at multiple strips and manually draw those cross sections, and it'll plot those all on a graph for you. But actually, VIP is going to automate that process, so it'll actually become you can apply those cross sections automatically through the test sequence, which will be a nice upgrade over standard TrueTest.
Okay, great. Another question here, how are color tolerances set in the software? For instance, if a manufacturer specifies a specific blue color for an interior light.
Okay, I think we do have a couple ways to do that. I think I have a slide that'll help illustrate it. Here we go. So actually in this case, one of the most common ways it is done is with, you can actually use the CIE chart. Some OEMs, for example, will give you the specs or requirements for the what's called the macadam ellipse that you can see here, for example. So it's a little small. There's a yellow ellipse here that was created by entering its coordinates and size. And then we can apply that region as a pass-fail for a POI or light strip, whatever you're measuring. So that's one of the easiest and best ways to do it within TrueTest.
Great, thanks. Another one here. How are the reflections of light from illuminated components on interior surfaces characterized?
Okay, so we characterize those in a very similar manner to the way we are characterizing the light sources themselves. So you can measure it in the same way with the same system and measure the max luminance or even size if that's important to you. And maybe most importantly, the delta luminance is the reflection, what's the data with no source, and what's the luminance with the source. So you can get quantitative data on how bad is that reflection really.
Alrighty, another question here about looking at backlit components. Can you detect if there's a dead LED on a diffused backlit component?
Certainly we can. We saw that in the slides when we were looking at the bare LED strips. We can do it through a diffuser as well using our auto POI tool and a threshold setting. So we can identify those dead or potentially missing LEDs behind the diffuser. Yeah, definitely.